Mm. Hey guys, didn't see you there. I was just too busy enjoying coffee out of my thermos. Today we're going to be talking about thermoses, so get excited. Today's video is not sponsored by Yeti, just in case you're wondering. It's not sponsored by anyone except for District 194, best district in the world, am I right? Anyways, moving on here. So, thermoses. One of the things you might notice about this one and then the other ones that you see on the screen is that they're all made out of metals. So, that's kind of weird if you remember anything about what we know about conduction, right? We know that things like metals and water conduct heat very well, meaning they're able to transfer it from one place to another. So, if you've got these things that are supposed to keep warm stuff warm and cool stuff cool, you don't want heat to be conducted. You want heat to be insulated so that it stays in the liquid and it doesn't just run out to the surroundings. So, why? That's kind of the main thing here that we're worried about. Why aren't thermoses all made out of nonmetals? Those nonmetals tend to be insulators. And the question we're wondering is, how do we keep thermoses cool if they're made out of conductors, right? Okay, so two things that you should already know here walking into today. Thing number one, a hot liquid will get cold due to conduction. And then thing number two is that a cold liquid will get hot either due to conduction or it could be due to radiation and sometimes both. Let's talk about hot liquids getting cold. Hot liquid is going to get cold when a slow, cold outside particles that are moving slowly bump into this fast moving particles, and then they both have a slower speed. So you have a fast thing hitting a slow thing, and then they average out their speeds. That's due to conduction. So that's how a hot liquid gets cooler. A cold liquid can get hotter due to conduction, so kind of the same thing. You've got these outside particles that hit a cold particle, speeding it up, and then they both are kind of, moving at the same speed. That's one way. The other way would be through radiation, right? So you got this cold particle, and then sunlight starts shining on it, and as that happens, it starts to heat up, it starts to move faster. So for cold liquids, conduction or radiation works. For hot liquids, really it's just conduction. Okay, so here's what I want to show you is I want to show you a picture of hot air and cold air, and kind of the idea is if there's nothing in between them, here's what's going to happen. We've got the hot air moving quickly, and we've got the cold air. You'll notice that that's moving fairly slowly. Now, over time, these cold air particles, you'll notice, will kind of collide with the hot air particles. And when that happens, because the particles have nothing separating them, the hot air is going to slow down and the cold air is going to speed up. So you're going to end up with something that looks a little bit more like this, where now over time, this thing called equilibrium is reached, and you'll notice that they're all moving around about the same speed here. You can see in the blue outline, those are what used to be the cold particles, and in the orange outline, that's what used to be the hot particles. So hopefully you can see here how they're now all moving at pretty much the same speed. That's with no insulator, what's going to happen over time. This will also happen with an insulator over time, right? Eventually, this coffee is kind of now cold, which is a bummer, but it's been out for like an hour or so, so it's going to get colder over time. Okay, so here's one example of insulation. This is just a styrofoam container. Um, yeah, so an insulator is just going to put matter in between my hot stuff and my cold stuff. That's really its job. And so let's imagine that inside this little container here, this little cross section of container, I've got cold stuff. Like maybe this is a styrofoam cooler, for example. And then my warm air is on the outside. What's going to happen then is that this insulator here, this kind of like, if we zoom in on the actual like thickness of the styrofoam, we'll see that one side is going to be really, really hot. That's the side next to the warm air. And this other side over here is going to be really, really cold. And it's going to stay that way so that not a lot of heat can transfer in the middle. The idea is that in the middle here, we have very, very far spaced out particles. So the hot particles moving super, super fast won't collide with the particles in the middle, and will keep the cold particles from not really moving faster. So an insulator is going to keep hot stuff hot, so it's going to have a hot side, and then it'll keep cold stuff cold, it'll have a cold side. That's how an insulator works. And then in the middle, we're trying to have as few collisions as possible. So here's just a quick review of what insulator and conductor mean, right? Conductor, materials that easily transfer energy. Insulators are materials that don't easily transfer energy. You should have this in your notes already. What I hope you can see here is, and I'm actually going to stop these particles, you'll notice that a conductor, the particles are actually closer to each other than an insulator. Because an insulator has more space between its particles, these two particles here won't collide as often as, say, these two particles here in a conductor. Just because there's more space, the collisions will be less, and then when there are collisions, it won't be as impactful, it won't be as forceful. You won't have that same amount change in energy, if that makes sense. So here's a look of if I put an insulator here in the middle between the hot air and the cold air. Something to keep in mind here, the insulator particles are spaced much further apart than shown. I couldn't show them hugely spaced apart just because I don't have the space on the PowerPoint to make that happen. But hopefully you can see here, we've got air moving fast, that's our hot air. And we've got our blue air moving slow, that's our cold air. Now, as we start, the first thing that's going to happen is notice how these particles are moving a little bit slower, not a very complete transfer of energy from the first layer. And then into the second layer, even less energy gets transferred from one insulator layer to the next one. And then kind of as we move forward now in the middle here, even less energy is getting transferred. So this stuff's going to stay cold, this stuff is going to stay hot. That's kind of what an insulator's doing. Okay, let's get back to the actual thermos. Here's a hydro flask. Here's what it looks like on the inside if you were to just cut it in half. One of the things you'll see over here is that in the orange here, we have some insulation. It looks like they have a spring to keep everything nice and centered. We have a rubber support at the bottom just to keep the thing in the middle there nice and in the center. And then you'll notice this little white area right here is actually what we call a vacuum. So maybe you heard of me talk about a vacuum before. We're going to really zoom in on this just to talk about it. So, wha-bam. There's my blue side. The blue side is with the liquid. There's my orange side. My orange side is with the insulation. And in the middle here, that's our vacuum. And what a vacuum in science means, it's not the thing that cleans your carpets. It means that you have no particles whatsoever. So think about it, like in air, you have very few particles, right? In a gas. But if you take all those particles away, you have a vacuum, which is just nothing. It's kind of like space, like it's just a void, like there's nothing there. And now this really helps prevent conduction because think about it, right? You've got your liquid particles over here trying to hit your insulator particles to kind of get, in this case, maybe the liquid's trying to lose energy, or sorry, gain energy because it's a cold liquid. We'll just say blue is cold. And then the insulator is going to try and give that energy to the liquid by hitting it. But if you have this space in the middle where there's no particles whatsoever, you can't really transfer energy through conduction because there's nothing to hit. So here, once again, we have our hot air. Here, once again, we have our cold air. And now we have our warm side of the insulator. We have our cold side of the insulator. But then in the middle, there's no particles. So the insulator particles on the left over here can't hit the particles on the right because there's this huge space in between them. And this is what a vacuum does. It's going to keep this stuff nice and warm because there's nothing over here to slow it down, or it's going to keep this stuff nice and cool because there's nothing over here to speed it up. So kind of the idea is one area is going to stay hot, one area is going to stay cold. And that's what this thermos uses. And it's just made of metal just to kind of like create that vacuum or to create that space where the vacuum can happen. Metal's a little bit stronger than some non-metals would be in this case, for example. So yep, you'll see that as I'm drawing that arrow, there's no real conduction. hopefully you learned something about thermoses today. Hopefully you had as much fun with this PowerPoint as I had making it. Have a great day, guys. We'll see you later.